Hello, everybody, and thank you for joining. My name is Russell Warren. I'm a product support manager for Dräger Safety. I'm based out of Houston, Texas. I've been with Dräger for just over 17 years. I've been in the industry for just over 35. And for those of you that know where Montana is, I got my start at Henry Safety Supply up in Billings, Montana, back in about 1984. So again, welcome to everybody. And if we do have some questions during the meeting, please type those into your chat. And at the end of the presentation, we'll circle back around to answer as many questions as we can in the allotted time period. We're going to take a look today at the DrägerSensors. This is a core for Dräger in that we do manufacture, design all of our own sensors within Dräger, and we use them in our products, and we don't sell those outside of Dräger to be used in other gas detection products anywhere in the world. So within our lineup of sensor technology, we do have electrochemical sensors, we have catalytic oxidation or catalytic combustible sensors, infrared sensors, and photoionization detectors. But based on the time frame that we have today, we're going to concentrate more and talk about the electrochemical sensors. So just to start off, a few basic terms that we use for EC sensors. Yes, at Dräger, we do use LEL for electrochemical sensors. We have hydrogen sensor that is electrochemical that measures 0 to 4% by volume or 0 to 100% LEL. And we can couple that sensor with one of our infrared combustible sensors. Infrared doesn't do hydrogen, so this gives us a more complete range of combustibles when using an infrared sensor. So LEL, the lowest concentration of gas needed to have an explosive atmosphere. So with hydrogen, that's at 4% by volume, and that's the range of our electrochemical sensor for hydrogen. When we talk about electrochemical sensors and toxic gases, we talk about parts per million. And just a quick reference there, to break down 10,000 ppm is 1 volume percent, or 1 second in 11.6 days. As we move forward in time, requirements for detection are getting much tighter. There are exposure limits around the world that are dropping like crazy. And so that's forcing our development to look more what we can do down in even the parts per billion range. So that's where kind of the future and some of these toxic gases is headed. There's electrochemistry, but there's also other technologies that can get us down into that parts per billion range for a number of different compounds already. Talking about percent by volume, generally when we talk about oxygen, we're referencing that in a percent by volume. Anywhere from 0 to 25% for a standard sensor, or even up to 100% by volume for one of our partial pressure type sensors. The response time of a sensor is also a very important component. Generally, response time is expressed as how much time does it take to get to a certain response. So we have a T90, that how much time does it take to get to 90% of your gas value. We have a T50 that's to 50%. I've also seen T20 response times in specifications. And this is important. Just recently, I was working with a customer on some SO2 detection, and the instrument that he was trying from another manufacturer had a response time that he was telling me that was in the 90-second range to get to 90% of his reading. And our sensor, the specification is less than 15 seconds to get to 90% of the response. So when you look at response times, there's a couple different things. On the safety side of things, in that if you have a faster response time, somebody's wearing an instrument as they're walking into an environment that can be contaminated, if you have a faster response time, you're going to get an alarm indication quicker and get back out to a safe area faster. You have a longer response time, that's going to allow you to walk much farther into the potential hazard source with that longer response time. So that is something that is important. There isn't a lot of manufacturers out there that actually publish their response times, but we do when we publish our response times in our sensor handbook that we have available for all of our available sensors. One of the other things we talk about with some of the DrägerSensors is relative sensitivity. We have a number of sensors, our organic vapor sensors, our phosphine sensor, amine sensor, even our chlorine sensor that are characterized for multiple gases. So in this example, I'm using our OV sensor that if it's set up and calibrated to ethylene oxide, it has a relative sensitivity of 1. If we're detecting one of these other gases, say propene, it has a 0.65 relative sensitivity. So meaning if I'm using a sensor that's calibrated to ethylene oxide and I'm detecting propene, I'm only going to get 65% of my actual value. So within our instruments, we can set it up so that we can calibrate with one gas, display another gas, and have a correction factor automatically applied. If you don't have that, you can use the relative sensitivity to do a calculation to get your actual gas value. So you take your gas reading, divide by the relative sensitivity to get your actual gas value. If you want to calculate a correction factor, you can take the one reference from the ethylene oxide, in this case propene, the 0.65. So you take 1 divided by 0.65. That gives us 1.54. That would actually be our display correction factor for propene. So you'll find this on, like I said, on a number of our sensors, just depending on what the application may be. So a little deeper look at electrochemical sensors. So electrochemical sensor, the response is based on a chemical reaction that takes place within the sensor. And the more gas that gets in the sensor, the greater the reaction that takes place, and the more signal is generated out of that sensor. And generally, it's a proportional signal and a linear response on the sensors in electrochemistry. So just an overview of a electrochemical sensor diagram in that the sensor, on the front end of the sensor, there's a porous membrane. There could be an additional filter on the front of that, whether it's a dust mist or a chemical filter, in addition to the porous membrane. Now, get into the sensor, the electrolyte, that's generally a sulfuric acid-based solution. The measuring electrode is where the reaction takes place, and that's where the signal output is generated, so that we can take that signal and we can amplify it, and we can condition it through calibration to give us our gas reading on the display. We have a reference electrode in the sensor that is there so that we can maintain a constant voltage on that sensor, so that as the gas concentrations increase, the stability of the sensor stays very even, so that higher concentrations of gas don't throw off the actual response of the sensor. And then there's a third electrode called the counter electrode that basically takes the chemical reaction that's taken place on the measuring electrode and reverses it, and pretty much puts that sensor back to where it started. So how do we make sensor specific? That inlet filter media, it can be, like I said, just a dust mist filter, but it can also be a chemical type filter, such as a charcoal filter. CO sensors generally will have a charcoal filter on the inlet of them, so that they will scrub out H2S. with no filter, CO sensor would respond better to H2S than it does to CO. The diffusion membrane, we can vary the pore size on that membrane to also control what gases actually get into the sensor. The electrolyte, we can vary the composition of the electrolyte to help pinpoint the gas that we're trying to detect. The electrodes in the sensor are made of precious metals. We can vary the composition of the metals to also control what reactions we get. And then generally we take it another step in that we also use a bias voltage on our electrochemical sensors. And with a bias voltage, we can further tune kind of like a radio tuning the station in, but we can kind of tune the sensor so that we can change the baseline threshold, so actually tune out some of the other gases that may respond on a sensor. So with that 3 electrode technology, that really helps us, maximize response and try to minimize the response to other chemicals. But in electrochemistry, we always end up with other compounds that seem to react on that sensor as cross interferences. And if you have gases that have similar elements or chemical properties, they can produce a positive signal on the sensor. And if you have gases with opposite properties, they might produce a negative reaction. Hydrogen on a CO sensor, and standard CO sensor is going to respond to hydrogen. Generally doesn't matter who makes the CO sensor. Yes, there are hydrogen compensated or hydrogen resistant sensors out there, but standard sensors, they're going to respond to hydrogen. But the negative reactions, one that was interesting always was NO2 and SO2 sensors. NO2 and SO2 have a negative response and on the other sensor. So if you had a situation where you had both NO2 and SO2 present, the reactions could basically cancel each other out, and you end up with a 0 reading on your instrument when you could have hazardous levels of both gases present. Just a quick look in that this is our older XS series sensor. This was a sensor, or is a sensor we use in our older Exam 7000. And we do have, for the some different sensors, different filter cartridges that can go in the top of the sensor. If that filter cartridge gets saturated, you can remove the filter and replace it without having to replace the whole sensor. And very similar with our new XXS series of sensors, we do have a number of sensors that we do have filters that can go on the inlet of those sensors. So again, we can filter out some of the cross interferences, but when that filter again gets saturated, we can replace the filter and not have to replace the whole sensor. So the expected lifespan of a sensor will vary. We do have sensors with very long warranties, CO, H2S, and O2. But just because they have a long warranty doesn't mean that that's all that they will last. We fully expect these sensors to last well beyond a 5-year period. So, and life isn't always determined by the gas exposure, more dependent on time and environmental issues more than gas exposure. There are exceptions. An ammonia sensor, for example, does have a dependency on the lifespan being determined by how much gas that sensor does see over its lifespan. So how can we get away with warranting our sensors, our oxygen sensor, for so long when most other sensors out there? Well, again, it's not dependent on the amount of gas our sensor sees. Other sensors on the market may have a lead base electrode, and that lead base electrode actually deteriorates as the sensor reacts to the oxygen. So once that lead electrode basically gets consumed, that sensor will stop working. It can work today, not tomorrow. It can die that fast. And we don't have a lead-based electrode in our sensors. Basically, we call our O2 sensors an O2 pump. So kind of what goes in one side, there's a reaction. I'm not a chemist, so but there's O2 goes in, it reacts, it creates the 2H2O. And then on the countered electrode, the 2H2O reacts to basically put everything back the way it was. Temperature, hotter temperatures can increase the speed of reaction, whereas slower temperatures can slow it down. Instruments do have temperature compensation within them to compensate for those changes in temperatures. Pressures, if you get change in pressures, you can have an effect on the sensors. Generally, I'm going to say more towards the oxygen sensors. Again, ours have a pressure compensation system in it. I was involved in a situation with a customer going down into a mine. They were using a sensor that would go into alarm as soon as they got in the elevator and went down into the mine. And it took 10 to 15 minutes for that sensor to stabilize once they got to the bottom. Testing our sensor in that application, we had no alarms on our instruments, and before we could open a door on the bottom, our readings were back at 20.9. Humidity. Humidity by itself isn't really that big a deal, except if it's a condensing humidity that could potentially condense over a sensor opening. In all my years of dealing with gas detection, I can't say I've ever seen that on a portable instrument, just because of the use and the motion and stuff of the units don't allow that to happen. There is a possibility in very dry atmospheres for extended periods that some of the water in the electrolyte can evaporate. That'll cause a reduced sensitivity. But if you get that sensor back into normal humidity, roughly 50% relative humidity, the sensor can actually resaturate itself and the sensitivity will come back. Okay, it says everything's been reestablished now, so don't know what that was all about. Hopefully we didn't miss too much, but smart sensors in the industry, generally smart sensors have a little circuit board on them that has information about the sensor. So when you plug it into the instrument will recognize the type of sensor it is and upload that information into the instrument. Our XS series of sensors, we do have smart series of sensors for the XS, which was again for our exam 7000. And these things had held quite a bit of data, and also the calibration information was stored on those sensors so that you could take a sensor out of one unit, put it into another, and get it up and running without actually having to calibrate it. So calibrations, per our specs, the big three, COH2S and O2, only require calibration every 12 months. Other sensors will vary from 3 to 6 months. This is dependent on the units being and the sensors being function tested or bump tested as they should be basically, daily prior to use. So sensors we have available, we have quite a number of our sensors available in the XS series. However, most of the development is going to our new XXS sensors. So the XXS sensors, it's hard to say, basically better response time, better performance than a lot of our XS series sensors. And these are not smart sensors, so all the data is actually stored on the instrument. And of course, they are replaceable in most of the instruments that we do offer. But when you do change a sensor out from one instrument to another, it will have to be recalibrated. And this is our growing list of sensors available for our XXS series. We've got quite a number, 30 plus now, characterized for over 50 gases. Pretty soon we'll have a new dual sensor coming out for CO and HCN, which will be available in our PAC 8500 single sensor unit, mainly geared towards the fire and responder market for our toxic twins applications. So I wanted to throw up a quick example of cost of ownership when we're talking about comparing apples to apples, kind of. And I just took into consideration an O2 sensor on this cost of ownership. And basically it's a 50 opportunity that was 50 exam 2500s versus brand X. And we're looking at a 5-year time frame for that those instruments, excuse me. So what we looked at, I just pulled up list prices, and our exam 2500 kit with charger has a current list price of $938. The brand X unit for standard 4-gas with charger was $695. They're looking to buy 50 of them. So our purchase price for that order was $46,900. The brand X was just under $35,000. So right out of the chute, we're $11,000 almost more than brand X. But after these 5 years, and the competitor here having to replace their O2 sensor at $225 a pop every 2 years, it ended up being a $57,250, almost $11,000 higher in the end. And if we were to go further and calculate in other sensors, gases that are used, how much time it takes, how much gas flow it takes to test a unit with bump testing and calibration, that number and that difference just continues to get bigger. So just kind of summarizing things here, that the warranty on CO, H2S, and O2 sensors, longest in the industry, long times between required calibrations, very wide variety of gases and vapors detected. Our O2 sensor is not a consumptive-based reaction, so we're going to get extremely long lives on our O2 sensors. And we do actually have units in the field with 10-plus-year-old O2 sensors that are still working almost like brand new. Again, the fast response times gives us that higher safety level I talked about, and also translates to less gas needed when you're actually doing the function and test and calibrations. And as of December 1st, 2018, the O2 CO and H2S sensors, XXS series, when we deliver those installed in a multi-gas monitor, they're now covered by a 5-year warranty. Our exam 2500, that always carried a 5-year warranty on these sensors, so they're actually, grandfathered in back to when they were originally sold. So that's kind of it on the sensors. One thing I do want to remind, don't forget about Dräger tubes or our CMS. SKC can help you out with all your needs. And current program provides for free shipping on ground shipping on tubes with orders of 10 boxes or more. So tubes are still a very important part of any safety program. So let's not forget those. So time to go to question and answers, and Chuck Knockreiner will be facilitating that session. So here we go. Take it away, Chuck.
Thanks, Russ. That was a very enlightening presentation. We appreciate your time and effort to do that. Thank you very much. We do have a couple questions for you, Russ.
Okay, I'll see what I can do.
Okay. Will there be any poisoning in the sensor? If so, under what condition does the poisoning happen?
Was that poisoning?
Poisoning, yes.
Yeah, not so much with electrochemical sensors. There is a chance that in some cases I have seen, say a CEO sensor that has been exposed to high concentrations of methanol, ethanol, kind of thing, that the filter on the sensor will take that stuff out, but only to a point. And once that filter gets saturated and that those compounds get into the sensor, at that point it's pretty much that sensor is going to probably need to be replaced. To get all that ethanol or methanol out of that filter takes a long time. So, and in some cases, you may not get it all out of that filter. It may just be there forever. Poisoning effects on a combustible sensors, that's something different to talk about. So.
Terry said, can you cover dust impact? He lost audio during that part.
Okay, well, dust impact, the big thing with dust is just that it, high volumes of dust could potentially block the sensor inlet and basically block gas from getting into the unit. So we just want to make sure that the units are tested, on a regular basis to make sure gas is still getting into the sensor. If the units are getting dirty, our instruments are a, IP rating for, IP67 for multi-gas, IP68 actually for our pack units. So if they do get dusty, you could actually take them and, run them under a cold water faucet with, a rag or a soft brush to clean them up and, shake off excess water, let them dry out, retest them, and you're back up and running. Nothing really else. Dust, the other portion of dust could be if you're dealing with grain dust or something. You got to make sure that the instrument does carry proper approvals for use in those environments, class 2 approvals if it's a combustible dust atmosphere.
Another one, Russ, from Dan. What is the best way to store a monitor for longer life?
Well, when you're storing an instrument, depending on your usage, but, we recommend, for, leave it on a charger. The charger's not going to overcharge it, but make sure it's in an area where you've got a good level of humidity, in that 50% relative humidity range. And that will definitely help maintain that sensor for quite a long period of time.
Okay. One from Kevin. Please explain sensor poisoning. Also, what will happen if it is exposed to 10 or 15 times concentration?
Again, I touched on poisoning earlier, but a lot of our sensors, CO sensors, H2S sensors, that if they get hit with high concentrations of gas, it may take, a few minutes for that sensor to recover once it's brought out to clean air. But we fully expect those sensors to recover and still be working sensors even after those high concentrations. Not all sensors in the market today can withstand high concentrations. We have a customer that actually, they'll use a standard CO and one of our high concentration CO sensors, which is a 0 to 10,000 ppm sensor in the same instrument. And they will actually, go over range on the high concentration sensor And once the sensors and once the instrument's brought back to clean air and the sensors clear out, you put it back on a test station, and calibration is generally within a ppm or so of your target value. So our sensors stand up very good to these high concentrations. The ammonia sensor would be, one sensor that high concentrations, will have a detriment on that sensor and its overall lifespan.
Thanks, Russ. There were two other questions, but they concern the same thing. One is about, it's pretty much about calibrations and the difference between what is really required of your instrument and will a bump test suffice?
Well, depending on the type of bump test that's done, from our standpoint, there's a quick bump test, which is just an exposure to gas to make sure it goes into alarm. Or there's an extended bump test, which is actually more of a calibration check, which is we're looking at the target gas value within a plus or minus 10 to 20% tolerance. And typically, if you do an extended bump test and you fall within that tolerance, you're good to go. You really shouldn't need to recalibrate that instrument. If you're outside that tolerance, that's what would drive the need to do a recalibration on that instrument.
Okay, and that you would do that prior to every use?
Well, by legal definitions, we do recommend testing a unit prior to use. In the real world, that doesn't always happen, but test it prior to use or test it as often as you can just to make sure. If it's been dropped in mud or water or suffered a severe shock or something, we do recommend doing a quick test after any time of physical impact or anything, just to make sure everything's still working as it should.
Okay, and we're out of time, but before we get off the webinar, I'd like to wish everyone a healthy and happy 2020, and stay safe out there. We appreciate it. Do you have anything additional to say?
I would second that. These times are tough, but we stick together. We'll make it through. Just make sure you stay safe and stay healthy.
Thank you. Thanks again, Russ. And that's it for now. We appreciate your attention. Thank you very much. Bye-bye.
You're very welcome. Thank you, everybody.